And so now the sort of last step here is pretty much the same as what we had before. I can find. Yep. So let's put together all the things that we have now so far. We have our v of x and y is going to be our x of x times y of y. And so if I put all that together, I have a cosh kx times c sine of ky. And just like before, a is a made-up constant, c is a made-up constant, so I can combine those. I can combine a and c, and I'll plug in my my expression for k. So what I end up with at this point so far is g hyperbolic sine of n pi x over a times regular sine of n pi y over a. Okay. And so now the only boundary condition that we have, we sort of combine together boundary conditions 3 and 4, but we still have to figure out that that x at b is that constant. And so we apply our final boundary condition that v of b y is equal to that constant there. Right? And so just like before, if I do that, I get sort of v naught is equal to g cosh of n pi b over a sine n pi y over a. And I can't, there's no value that I can pick for g that will make this happen. And so instead, we must use a sum with all those n's that we had for k. And so instead, we're going to end up with sort of a v naught equals big ol' sum. And each one of my g's could be different for n equals 1 or n equals 2 or n equals 3. Okay. And now, even though I've made it more complicated by having this sum, now I just need to figure out what the GNs are. And this is exactly like what we had with the previous part, except now I have this cosh thing sticking in here, but this is just a constant, right? This is a b. There's no x or y in here. And so instead of solving for the GNs, I'm just going to kind of solve for this whole thing. And this is exactly like the previous example, where we use this thing called Fourier's trick. And again, I don't want to necessarily go into the details of Fourier's trick, but last time we used this thing where we did this integral, and we figured out what the integral was, and it was a straightforward integral, and we got g of n equals something. And so the same thing applies here, except instead of saying g of n equals something, it's g of n times cosh equals that same value. So we get g of n times cosh equals 4 v naught over n pi for only the odd ends. If you're not sure where I got that, go back and look at the example from the previous day. You'll see that we had gn equals 4 v naught over n pi. Now we just have this extra sort of constant bit that's out front. And so now we can just sort of solve for gn here and say gn is 4 v naught over n pi times 1 over cosh. Because this is a b in here, it's not an x, so It's an ugly constant, but it's just a constant that we kind of drag along the way here. And so finally, we can put all that together and get our complete final answer. And that would be 4v0 over pi. We have our big sum. Remember that this only works for odd ends. So we don't have n equals 2, 3, 4 all the way to infinity. And we have 1 over, we had the n, and then we can't forget about that extra cosh we have in the denominator, times the actual function itself. So we have the regular cosh that has the x in it. Times sine of n pi. And that is our solution. Now, again, that looks ugly. There's a lot going on there. The most complicated step, which is this Fourier's trick, is not something that's something that you should that you can look up or see in math physics or something like that. The important thing that you should be able to apply here is to look back at these boundary conditions, right? You should be able to look at a problem, write down the boundary conditions based on what's given to you, and then go through this separation of variables and apply them, right? So if you have a situation like this where you have, y at 0 is 0, you can kind of look at that and say, that's going to make one of those terms go away. The same thing here with the sign, the symmetric or anti-symmetric, odd or even functions, that sort of stuff. All of those things are applying these boundary conditions to these simple exponentials and sines and cosines here. This last step, the very last step where you have to do this Fourier's trick, is sort of an extra step that you will learn more about in math physics. And that is about it. Hope that was helpful.